So we are talking about chapter 5. Right about here. And so we're talking about transport. The rest of the chapter is going to be about transport. So just kind of a little bit of a disclaimer for those of you guys online. If it sounds like my voice is muffled, it's because I'm wearing a mask today. You can hear obviously by the sound of my voice, I'm a little froggy. So that's the reason why I'm trying to stay away from you guys. So if you have a hard time hearing me, just let me know. I think I've got at least a good 6+ feet on the nearest person. So you guys are okay. So what I want to do, however, is I want to take a look at the passive transport piece, but I want to take a look at all transport, right? So one of the things that I want to do is I want to couch this with respect to some energy, because we're already talking about energy. So one of the things that I want to do is I want to sort of wrap some of our ideas around this. There's basically the rest of the chapter is going to be on transport, and what so what we want to do is this is the kind of the point where I kind of like to start to sort of frame and sort of pull together some of the ideas associated with energetics and actually embedding some of that knowledge into our discussion. So when we talked about last time, just to kind of refresh your memory, we were talking about the membrane stuff, right? So we're talking about inserting proteins into membranes. We're talking about the transmembrane domain. And we also talked a little bit about the fact that there's a lot going on in the membrane itself. Remember, we talked about the archaeology thing. That was kind of like one of the last things we talked about. And now what I want to do is I want to frame some of this. I'm going to see if my Apple Pencil is charged up enough. This is one of the drawbacks of being gone for a week, right? So my Apple Pencil is pretty much dead. Let's just see how dead. Oh, not too bad. That thing's still alive. So here's basically what we want to do. So we're talking about energetics, but what I want to do is I want to drop a slide in here, and I kind of want to start writing. I'm going to do one of these notorious writing slides that I tend to do for you guys sometimes, and I'm sure you guys love. Okay. Hold on one second. For some reason, PowerPoint is not highlighting any of my stuff. There we go. That's what I want to see. And I mean, it'll take a few extra minutes, but it's a time that's worth spending. By the way, if you're wondering where we are right now in chapter 4 and 5 is like the heart. It's like the bullseye of 1111, right? So it's like when you're talking about skimping on chapters, these two chapters aren't the ones you skimp on. These are like the core of bio. So we want to take a look at transport. Now in cell transport, you have three main types of transport. You have passive transport, and there's active transport. And then there's what's called bulk transport. So first of all, what I want to do is I want to kind of sketch these guys all out together, and then I want to kind of go a little bit deeper, and then I want to start tying in some of the energetic stuff. So passive transport, basically, when you take a look at it, the passive transport itself is essentially the movement of molecules without the need for energy. And there's a couple of different types here. So the first one, which is simple diffusion, is the movement of small nonpolar molecules from high concentration to low concentration. So what's an example of a small nonpolar molecule? Well, you're breathing one right now. Actually, you're breathing two of them actually right now. Yeah, oxygen is one of them. Remember when we took a look at oxygen, because the two oxygen atoms, they have the same electronegativity, right? So you basically have a stalemate. So they're non-polar. Carbon dioxide is the same, right? So basically it's got two oxygens on either side of it. And so you kind of have this sort of symmetry associated with that. So a good example of this is oxygen and CO2. Of course, this also means small like lipids and things like that. A good example of a small lipid would be like a steroid, right? Like estrogen, for instance, or testosterone, right? Those are our sex hormones. So those steroids are able to actually move into and out of the cell freely without any kind of encumbrance at all, right? So that's because they're lipids and they can just basically breeze right through that lipid membrane. And that's the reason why like an estrogen receptor is not an external receptor, it's an internal receptor, because it's a lipid and it can just freely go through in response to its concentration gradient, okay? So that's just simple diffusion. Then facilitated diffusion is basically the same kind of an idea, only in this case, it's the movement of small polar or charged molecules down the concentration gradient. And there's usually two different types here. There's kind of channel driven, and then there's carrier driven. We'll talk about each one of those. I don't want to expand on those just yet because we'll do that later on in the chapter. But this is basically how you get, say, for instance, water, right? Or like a sodium ion or something of that nature across the membrane, which is something that the cell needs. But because they're polar, that non-polar membrane is a problem, right? So it gets rejected by that non-polar membrane. So facilitated diffusion is basically a situation where you have movement of a small polar or charged molecule down its concentration gradient with the help of proteins. And it's either channel or carrier driven, mostly channel driven. And then of course, the last in this pantheon is osmosis, which is the diffusion of water. And what's the mantra of osmosis? You guys remember that one? Yeah, right. Salt sucks. So basically what this means is that water will always move toward the saltiest area because water is always trying to dilute things to equilibrium, right? Now, these are all downhill processes. That basically means they don't require any energy. And so when you take a look at it from energetics kind of a point of view, you'll basically have this kind of energetic curve. And it's kind of like going from a high energy state or a high concentration, right? So you're kind of up here, down to a low concentration point. So you're down here. And it's in a lot of ways, it's kind of like being at the top of a hill with a boulder, right? So if you take a look at that system, what do I need to do in order to get that boulder to roll downhill? Yeah, just let it go, right? That's a pretty steep hill we're on there. It's a pretty big boulder. It's bigger than me. Chances are, actually, I'm not strong enough to hold that thing in the first place. So this is kind of a little imaginary, right? But what's happening then? So once I let go, do I have to do anything for that boulder to roll downhill? No, it's automatic, isn't it? So the reason why it's automatic is because at the top of the hill, this represents its high energy state. At the bottom of the hill where the boulder comes to rest, this is its low energy state. So this is the downhill process, right? I don't have to put any energy into this because I'm going from a high concentration to a low concentration. So as long as I'm going from high to low, it's already spontaneous. So I don't have to do anything extra for it. Now, what about active transport? So active transport is basically the movement of molecules, generally solute molecules, from an area of low concentration. Notice the inversion. You're starting low and you're going high. And here you need energy in order to do it. So if you take a look at this, there's going to be two major types of active transport. One is ATP driven, where your energy source is coming directly from ATP. The other one is going to be concentration gradient driven. We oftentimes refer to this as coupled transport. We'll take a look at some examples of that in just a little bit. But when you take a look at active transport, this is you're starting off low and you're ending off high. So instead of going downhill, you're going uphill. Right, so here's your downhill process. And this is your uphill process. So take a look at me now at the bottom of the hill behind this boulder. What do I need to do in order to get this boulder up the hill? Yeah, I got to put some energy into it, don't I? I got to put my shoulder into it. So basically I have to add a lot of energy and I have to do a lot of sweat and labor in order to get this boulder uphill. Because I'm adding to it, right? So because it's going in a direction that it doesn't want to go, right? So it wants to stay here and it's like low energy state. So this is its low energy state down here. And I'm trying to get it to go to a higher energy state. Now, one of the things that I always like to do this is because oftentimes you tend to talk about passive transport, and you oftentimes will talk about channel-driven passive transport, especially if you go into A&P. And a lot of times you'll talk about sodium channels and calcium channels and things like that. But one of the things to always remember is these things come in pairs. Remember, biology, our reactions are reversible. So whenever we're talking about a forward reaction, look around. There's a reverse reaction laying not too far off. In this particular case, if there is a passive transport system, that is to say, if you got a boulder at the top of the hill, it didn't get up there by the magic boulder fairy, right? Somebody had to put that boulder up there. That is an energetic system and an energetically unfavorable system, right? So it had to have gotten up there somehow. And the somehow is active transport. So whenever you talk about things like sodium channels and things like that, always remember that in order to get that boulder up to the top of the hill in the first place, you had to have had active transporters building that system. So if I want that boulder to roll downhill, then I have to first set my system up by pushing that boulder up the hill. Then I can let go, the boulder rolls down the hill. And if I want to do that again, guess what? I got to push it right back up the hill again. I have to reset the system so I can roll it back down. So as many times as I want to roll this boulder down the hill, I have to reset the system by pushing it to the top of the hill in the first place. So whenever you see things like a sodium channel that's making use of passive transport, letting sodium ion passively flow from its high concentration to its low concentration through a channel, always remember that not too far off, there's a sodium active transporter that's building that concentration gradient in the first place. Okay, they go in pairs, and it's always good to make sure you keep that clarity. Now, the last one is bulk transport. So this is basically the movement into or out of the cell of large macromolecules. And you have a couple of major types. So you have endocytosis. This is movement into the cell. And within the endocytosis grouping, you have three major types. So you have what's called phagocytosis. We've already seen an example of that one. That's when a cell engulfs something else, right? So this is cell eating. And you have penocytosis. And this is kind of when you take little sips. You're not just engulfing something big, you're taking little sips, right? This is called cell drinking. And then you have receptor-mediated endocytosis. This is where you specifically select you just select the molecule with a receptor, a specific receptor. So those are the three different types of endocytosis. We'll talk about all three of those later on in the chapter. And then you have exocytosis. And this is basically movement of macromolecules out of the cell. You've already seen exocytosis, by the way. Yeah. This one? Receptor-mediated endocytosis. So you've already seen both of these, right? So you've already seen phagocytosis. We use that as an example of when a cell engulfs something and then it kind of internalizes it and kind of packages it into like a food vacuole that fuses its lysosome to it. Okay, so we've seen an example of that. We've also already seen an example of exocytosis as well, right? So when that secretory vesicle fuses with the membrane during the secretory pathway, that's exocytosis when it releases out to the outside world. So the basic what we're going to do is we're going to take a look at passive transport first. In this case, you're diffusing either a solute molecule, if it's like simple diffusion or facilitated diffusion, down a concentration gradient. So going from high to low concentration. Or if you're water, which is also part of the passive transport grouping, then you're going the opposite direction, right? So you're going toward the salty area. So salt sucks. Now, one of the things that we kind of did, remember in the lab, we used this as an example. And this was basically taking like whole blood or food coloring, more interesting than blood, right? So in this particular case, you can see you take a drop and you put it in a beaker of water. And so in this particular case, where's the high concentration in the system in B? Right? In the little droplet, right? So that's your high concentration. It's low everywhere else in the beaker. So we already know then that in this particular situation, you have a pretty steep concentration gradient, right? So it's pretty high in the droplet. It's pretty low in the rest of the beaker. So what's going to happen? It's going to move by diffusion from high to low. So it's going to basically go through the rest of the beaker. That's the reason why you see these guys kind of moving outward. And now after a little bit of time, you can see in C, it started to diffuse out a little bit, but it's still not there, is it? It's not done yet. So you can still see it's still high in the droplet. It's still fairly low in the rest of the beaker, but it's not quite as steep anymore because you've had a little bit of diffusion. So now what's going to happen is your high is not as high as your low. So it's a little shallower now. And then eventually what's going to happen is this one right here, which is equilibrium. At this particular point, both of your concentrations are equal. And that's basically what diffusion wants to do. It wants to flow from high to low until both become equal. So here's a little bit about the energetics that I want to kind of tie into this, right? Because we already talked a little bit about energy state. But there's something that drives this that kind of governs pretty much everything. And it's actually one of those things where we get the laws of physics kind of interacting and intersecting with biology and sort of setting the rules of the road. And this is actually something that when you're thinking about constructing a biological organism, this is something you have to be aware of. So in the universe and in physics, there's a universal law. There's actually 3 of them. There's actually more than that. But the 3 that I'm interested in are the laws of thermodynamics. Anybody run into those guys? One in particular is the second law of thermodynamics. So the second law of thermodynamics is what's referred to as the entropy law. So this is basically a situation where we have the definition of the second law basically says that all systems in the universe, because it's a universal law, proceed to a state of maximum disorder, which is called entropy. So it proceeds toward a high entropy state. Well, that's all well and good, but what does that really have to do with anything? Well, as it turns out, the state of maximum disorder, this state is also your lowest energy state. Remember what the boulder did when we let go of it? What did it do? It went down, right? But it went from a high energy state to what? To a low energy state. So the reason why it goes from high to low, the reason why the boulder actually moves forward until it comes to rest at the bottom is simply because it is obeying the second law of thermodynamics. Because as I hold it at the top of the hill, it is in a higher and therefore an unfavorable energetic state. If I allow it to do so, then it will naturally, according to the laws of the universe, acquire a lower energy state. That's the reason why it rolls forward. This is also the reason why I don't have to do anything in order to get it to do that, because going to a low energy state is an automatic, spontaneous thing. You have to do nothing for it. It's free because that's where the universe wants you to go. Okay. Now, if I want to go the opposite direction, Because if I want to go to a state with a lot of order, then what do I have to do? So I have to go from a low energy state to a high energy state, which means I'm going to have to so if I want to go to a high energy state, what do I have to add? Who is full of energy, right? If you go from a low energy state to a high energy state, I'm looking at active transport now. If I want to go uphill, what do I have to do to that boulder? I have to add energy to it. Notice what's happening. I am taking that boulder and I'm putting it in an energetically unfavorable state. I can do that, but it's going to cost me. I have to take my energy. I have to figure out how to find energy somewhere and add that to the system in order to get this system to acquire an unfavorable energy state, because the entire universe is telling it not to do that. Does that make sense? The reason why we take a look at that, and the reason why we like to couch it with respect to order, is because take a look at your body. Is your body an example of order or disorder? You may feel disordered, but that's different. That's different, right? Think about all the things that your body has to do. Do you think your body is an orderly unit with a lot of order in it, a lot of control and regulation, or do you think it's a disordered mess? So it's all connected, right? So basically, your body and the body of an organism, all that coordination we've been talking about the cells and things like that, all of that flies in the face of the second law of thermodynamics. So if you think about it, the entire universe wants you to acquire a state of maximum disorder, which for us would look like what? Not alive? Death? Yep, keep going. What happens after death? Yeah, decomposition, right? So complete and utter disorder of our molecules. That's our lowest energy state. That's what the universe wants you to be. So when you are building this massively intricate body with all these moving parts to it and all this control and regulation, what do you need in order to acquire that higher energy state? Well, here's the question. How many of you guys have eaten today? Okay. Some of the brave souls admitting it. Right? It's okay. It's not a bad thing. How many of you guys plan on eating again before the day is over? How many of you guys ate yesterday? Apparently, we all have 2 people eating today, so the rest of us are in varying states of starvation. Okay, fair enough. That's okay. And normally, when you're not fasting, yeah, because of holidays and things like that, that's yes, okay. And so, are you going to eat tomorrow? How about the day after that? Do you normally eat more than once a day? Wow. So it sounds to me like, right? So it sounds to me like that's kind of a lot of what we do is eat. Why are you eating? Yeah, you actually have a little energy stick right now. Right? Right. And you got also a little energy cup right there, right? So yeah, you're basically acquiring energy. Why do you need a lot of energy? Because in order to create a body that is highly ordered like ours, that is flying in the face of the second law of thermodynamics, it requires us to have a lot of energy to do that. Basically, your body is like a boulder that you are pushing uphill. It requires energy. And when you eat, you're acquiring that energy in order to do that task. So energetics wise, everything is wired to go to this lowest energy state. And that's everything. That's literally everything. Think about things that depreciate, right? How about a car that depreciates, right? That's the second law of thermodynamics. You're basically acquiring a more disorderly state. Buildings, if we walk away from them, they start to fall apart, right? They start to deteriorate. And so that's the second law of thermodynamics. It's acquiring a randomized state when it deteriorates. What does it require for us to keep these buildings all nice and pretty? Energy. We have to pay somebody to work and work hard to maintain the buildings. Why? Because the default system in the universe is to fall apart. That's the reason why passive doesn't require energy, is because it's simply just let go and let the universe have its way. And then when you want to build order or structure, then you have to basically go against the universe. And that's going to require energy to do that, right? You're pushing the boulder uphill. So think about it. We've talked already in chapter 4 and 5 about a lot of structure, right? There's a lot of things that have structure to them. But remember, structure doesn't come for free. Structure has a cost to it. So whenever you're building a structure, what you're doing is you're opposing the second law of thermodynamics and you're opposing order in the universe. When the universe wants disorder, that's going to cost you. So anything or any structure that you want to build in the cell is going to require energy, which is the reason why when building a biological organism, the first place you start in those big biological questions of life list is you start off with your energy plan. So what kind of energy am I going to have so that I can build structures with it? Okay. This is basically also the reason why we have a lot of wear and tear on our bodies. Aging is not mysterious, actually. It is simply our bodies progressively succumbing to the second law of thermodynamics, progressively approaching a state of disorder, a low energy state. And our body can only fight against that for so long, until it finally starts to give up. So that's basically what's happening. So then when you take a look then at the membranes that we have, remember these membranes are nonpolar because of those tails. And because they're nonpolar, basically what that means is that nonpolar molecules like oxygen and CO2 or lipids, small lipids, will basically move back and forth pretty much freely. However, if you start to get small nonpolars, this basically is precluded. So this basically is blocked by the nonpolar membrane. And it gets even worse if you're charged, right? So just gets harder and harder. But here's the problem. You still need some of these small nonpolar molecules, don't you? The cell still needs ions like sodium, for instance, and calcium. So there's still some ions in there that your cell needs. So you have to solve this problem. That's where the transport's coming in. That's the reason why we have transport. And that's the reason why we have to create a way to get these molecules into the cell, right? And that's where facilitated diffusion comes into play. So with facilitated diffusion, basically what we have is largely the movement of your small polar or charged molecules. They're still going to be moving from high to low, but they're using either channel proteins. This is basically for high output movement. or carrier proteins, which is basically selective movement. And it's limited movement. Typically speaking, in passive transport, I'd say 9 times out of 10, what you're looking at, what you're talking about is channels, not carriers. In active transport, most of what you're talking about are carriers, not channels. Okay. Let me explain the difference between a channel and a carrier and how they move stuff around. A channel is just basically like the door, right? So basically it's a hole in the membrane, and it's got this nice sort of habitable zone inside this little pore, right? So we saw how you get a pore using those transmembrane domains. And the insides of those pores you can make habitable or hospitable for an ion, for instance, like a sodium ion. Well, typically speaking, if you want a massive influx or a lot of movement of the sodium ion at once, then you're going to want to go with the channel protein. Here's the reason why. Channel proteins and carrier proteins are a lot like in the East in some of those river systems where you have roads that are blocked by rivers or bodies of water. And in the East, they have ferry systems, right? They don't have this in the West. So in California, there's no such thing as ferries. So this is all just my learning from afar, right? But when you take a look at one of those ferry systems, I don't know if any of you have been on them, but a ferry boat basically is designed to basically transport the cars from one end of the body of water where the road stops to the other end, right? And that's kind of what it's supposed to do. Oftentimes it's associated with large expanses of water that are just too big to span a bridge across, okay? Well, here's the problem. What happens is if you basically got a ferry, it's got a limited number of spots for cars, right? And so that's going to limit how much you can do. Not only that, but there's also going to be a certain amount of time associated with you taking it over to the other side and then coming back. So if you're actually sitting there waiting to get on the ferry, you could be there for a while because you're waiting for that boat to load up, and then it goes across and delivers one batch of cars, and it has to come back and has to pick you up, right? But it's always going to be limited because it's only going to have a certain number of cars that it can carry. And that's what the carrier is like. A carrier only has a certain number of pockets, if you will, that can accommodate the molecule. So it's like it can grab onto 2 of them and then move it, and then 2 more and then move it. So really what you have then is you have a slow trickle of whatever this is, right? So it's low output in nature. But if you take a look at something that requires a lot of sodium ion moving very quickly at once, kind of like a tsunami, you need a bit more movement than that, don't you? You need higher output. So what do? Instead of the ferry boat ferrying cars across the body of water, what you do is you build a bridge. The bridge basically is a thoroughfare, just like a channel is, that allows as many cars as you get through there to just basically fly on through. And so that way you get maximum output of sodium ion going through from one side to the other. And so that's the reason, normally speaking, when you have passive transport, most of the time we want high output movement. And that's the reason why we tend to use channels. The only time you see carriers is when you kind of want to balance things out a little bit. If you think about it, sodium can be quite dangerous if you're moving it in a tsunami fashion because it has a positive charge. And whenever you start moving charge around, that can create like static buildup, and you can kind of get this sort of static electricity charge thing. We'll talk a little bit more about that in just a second. And that can be a bad thing. So from time to time, you kind of want to balance those wild swings of charge by using a carrier, which kind of will let some other positive charge sort of counterbalance it a little bit. And so that's what you tend to use carrier proteins for in passive transport. But each ion has its own channel. So for instance, the potassium channel doesn't get to go down the sodium channel, right? I mean, the potassium ion doesn't get to go down the sodium channel. The calcium ion doesn't get to go down the sodium channel. It has a separate calcium channel that's designed for it. Okay. So what that does then, since you have a specific channel for a specific ion, that gives you a lot of selectivity in what you're going to be making yourself permeable to, what you will allow into you as a cell or not. Okay. So that's facilitated diffusion. Probably the majority of what we talk about are ion channels. And when you take a look at ion channels, you have to remember that when you basically take a look at these ion channels, you're talking about stuff flowing from high to low. Now here's a problem, right? You use the boulder example, right? If I basically allow that boulder to roll, it spontaneously rolls downhill, doesn't it? But what happens if I want to control how that boulder rolls downhill? Well, I'm going to have to come up with something, aren't I? I'm going to have to figure out how to control and manipulate how that boulder rolls downhill. Ions are the same way, right? So when you basically remove the structure for ions, they're just going to flow like a flood from high to low, and you're not going to have much control over it. So how do you control these concentration gradients, right? Because the second you build them, they're going to want to flow downhill, right? It's just like you can feel it in the boulder. As you're pushing the boulder uphill, you can feel the boulder wanting to roll downhill and squash you, right? So what's the question? You have to come up with some sort of a mechanism to control that boulder a little bit so you can get it up the hill to where you want to position it to. Well, ion channels have a similar type of a control mechanism. And this is something that I refer to as channelology. Now, if you go into AMP, you will run into these. This is basically how things are controlled in a channel. Think about it. If you've got all these high to lows, you kind of don't want these things to just start flowing downhill, like without some control, because it'll get a little crazy. It'll get like you'll just get flooded all over the place. So you want to have some control, some say-so about how these things are moving back and forth. And that's what this particular slide is about. It's about the control of flow. Through a channel. And you'll see a lot of these in AMP. The first one is what I call osmotic control. This is basically where osmotic conditions control the movement of the molecule. And here's a good example. So here's my membrane. Here's my channel. There's the rest of my membrane. So on one side, I'm going to have a high sodium concentration. On the other side, it's going to be low. So which direction is sodium going to move? So this is the outside, this is the inside. Yeah, it's going to rush in, right? So if I want to get sodium to come in, then I set up the concentration gradient so that sodium naturally wants to flow from high to low. So let's take the same system though. I've got another open one. Now let's go ahead and take a look at the movement of water. Which direction is water going to want to move? That's osmosis, or the mantra of osmosis is Yeah, so it'll do what? Yeah, it'll move from inside. Exactly, right? It'll go from inside to outside in response to what? The sodium concentration, right? So notice what you did was you controlled the movement of water into or out of the cell simply by manipulating the osmotic environment. And this is actually how water moves throughout the cell. It's an open system, it's an open channel. And all you simply do is just manipulate the salt concentrations with your active transporters, building different salt piles in areas that you want your water to go. And then the water will just freely move out of the cell in the direction that it wants to go, like in this case, the salty area. So notice what I did is I controlled the flow through this channel simply by manipulating the osmotic environment. Okay. So that's an example of osmotic control. The second one is, the next three are basically using what's called a gating system. So the first one is called a ligand gated channel. This is where a chemical signal opens a gated channel. So here is my membrane. Here's my channel. It's got a gate on it, but that gate has a little pocket. It's designed to bind to a ligand, which is a chemical signal. So this chemical signal will come in and it'll bind to that gate. When it does, it changes the shape of the gate, which will open it up, and then in will rush. And let's take up our same system, right? We have sodium that's high on the outside and low on the inside. So when that gate opens, because of that ligand, what's going to happen? Sodium's going to rush in. What if I want that sodium to stop rushing in? Well, I just basically take the ligand off of the gate will close back up, and then it'll block your sodium from rushing back in. So you use a ligand, a chemical, to change or to open up the gate, the floodgate of that sodium channel. The next one is called a voltage gated channel. This is where a change in membrane potential opens the gate. So what I want to do is I'm going to draw a ligand gate first, and then I'm going to add a voltage gate, and maybe a couple of them. Like that. These are V's. So here's how a voltage gated channel works. So let's get it started first, right? With the ligand gated channel. So here's what I'm going to do. This is going to stay the same. My sodium concentration is high on the outside. On the inside, it is low. Now, there's a couple of things I want to explain. First of all, right, it's this idea of membrane potential. Membrane potential is essentially the voltage of a membrane due to the positive charge ion. So what happens when your transporter puts the sodiums on the outside? Remember, you're not just moving sodium, you're also moving positive charge, because sodium is a positively charged ion. So when I say that you have a positive charge ion that's high in concentration on the outside and low on the inside, Electronically, what I'm also saying is that the outside of the membrane looks a little positive relative to the inside, which looks a little on the negative side. That disparity between charge separated by an insulator, right, that nonpolar membrane, is membrane potential. We can actually measure it. Membrane potential actually comes out to be about minus 70 millivolts. Okay, we do this a lot in muscle physiology. Okay, let's take a look at it. So first of all, a chemical signal comes in to the ligand gated channel, binds to it. That gate opens up, and then what happens to the sodium? It rushes in, doesn't it? But let's forget about it being sodium for a second. Let's just think about it as positive charge. So all that positive charge comes rushing in. That's going to have electronic consequences, isn't it? So what that's going to do then is it's going to start to flip this charge, this membrane potential. It's going to make the inside look more positive and the outside look more negative. When you do that, when you flip the charge, it's a process called depolarization. When that charge flips, that is a voltage change. And that voltage change is what these voltage gates sense. So they feel the charge flip that's happening just above them. And then what that does, that pops open their gate. And then guess what? More sodium comes in, right? That is saying more positive charge. But what does that do to the adjacent membrane? That flips the charge, doesn't it? That changes the voltage, which is sensed by the next voltage gate, which then pops open and then in rushes some more positive charge, and so on and so forth. And then that's positive charge is going to flip the next membrane, and that's going to open up this voltage gate, and then so on and so forth, or as long as you have voltage gates. So notice what's happening. What you have is basically this kind of progressive domino-like roll of these sort of depolarizations, with this wave, if you will, of depolarization. By the way, that mechanism that I just showed you is exactly how a neuron sends a nervous impulse down the axon. So when it sends that electrical signal, what it's sending and the way it sends an electrical signal is simply by the movement of sodium ions. And that creates this depolarization event, and that depolarization event is what rolls down the axon to your muscle cells to get your muscles to contract. Okay. So when you get to AMP1, just act surprised. Then we also have mechanical gated. So these guys will basically use physical distortion will open the gate. So let's imagine we have, here's our gate. And we have kind of like a little spring that's attached to a distortable protein. So let's imagine, so this is a distortable protein. So what happens is physically, if this protein bends and bends in this direction, what's going to happen is it's going to pull this little coil part, it's going to pop open that gate. And this is basically how you hear. The way you hear is with physical distortion. So you have membranes actually in your inner ear that will physically distort. And when they do, they basically pop open the gate of the channels, and that allows either a little bit of sodium in or a lot. And so depending on how strong the distortion, if you let just a little bit in, then you'll hear a certain pitch. If you let a lot of it in, you'll really open up that gate, and you'll hear a different pitch. How do you get the distortion? Simple. It's the waves of the air. So the air waves, the compression waves of the air that's created by sound, hits your eardrum. Your eardrum basically will vibrate as those compression waves are hitting your eardrum. And then what they do is they basically kind of create like a little wave machine in the endolymph in your inner ear. And they basically transfer the compressed air that's hitting your eardrum. And they create like a little wave-like pattern in the fluid in your inner ear. And that fluid is what distorts the membrane. If it's a hard pull on that, then it's going to really distort the membrane. You're going to hear a certain pitch. If it's a gentle pull, then you're going to hear a different pitch because it's only going to be popping that little gate open just a little bit. Okay. So those are really important ways of how to control what's going through the channel itself, right? You don't just want, and this makes a lot of sense, right? I mean, it's, you don't just have wide open holes in your house where anything just come on through, right? All of the holes in your house, windows, doors, things like that, are all regulated and controlled. And you can decide when to open them up and when not to. So you have a lot of control on your apertures in your house, right? Some of them are gated, some of them are locked down, right? So there are certain controls for everything in your house. And the same thing is also true for the cell. Okay. So here's kind of like what your channel looks like. So you can see basically you've got high versus low. So you can see it's going to go in this direction. If you want to go the opposite direction, it's pretty simple. You just build the concentration gradient in the opposite direction. That's simple. In this case, you're going to go in the opposite direction. Why? Because you're going from high still to low. All right. So that's kind of nice. That basically means there's directionality. So I can decide which direction to aim my concentration gradient to either get stuff to come in or to get stuff to go out. Okay, that's really useful. We've already seen how we can actually increase the diffusion speed, right? By increasing the pitch or the steepness of high versus low concentration. Now we can actually point it in specific directions. Okay, that's also very helpful. Now, carrier proteins, like I said, these guys are just going to be grabbing onto a single molecule at a time or a couple of molecules at a time. But, you know, if you've got like an entire state of New York trying to cross a body of water, you're not going to be able to go any faster than the ferry can manage, right? So the ferry is going to fill up, and then they have a certain processing time where they can get across the body of water and they come back. And they can't go any faster, right? It doesn't really matter how much you yell at them. They can't physically go any faster because they can only hold so many. And they can only go so fast, right? So that maximum speed that they have is what's referred to as saturation. So you can only grab onto so many things at a time and you're full. You just have nothing else left to grab onto. That's what's called saturation. So if you take a look at a transporter, for instance, basically you see it grabbing onto a molecule over here. And then what it'll do is it'll change shape, usually the molecule, the protein will. And when it changes shape, it'll basically dump it on the outside. But if you notice, it only has the room for one. So it can't grab any more than one. So it can only do one at a time, right? So this is the reason why your transport is limited, because you're limited by just how many you can grab. In this case, you can only grab one at a time. Okay. Which is one of the reasons why, like if you're a neuron and you need a high influx of sodium in order to get that membrane to flip, that charge in the membrane to flip, going with carriers is not a good idea, because it's going to take like forever to get that membrane to flip, and your nervous impulses will be so slow. It's like, will be like banana slug territory, right? So that is our diffusion. And of course, now let's go ahead and wrap it up with our osmosis, right? So this is our diffusion of water. That's basically what you're looking at. Of course, that combined with the idea of salt sucks kind of pretty much gives you a working ability to sort of deal with osmosis. It's always going to be going toward the salty area. And so this is kind of an example here. So here you see we have a solute molecule, urea, that's in what's called a U-tube experiment. So this is a semi-permeable membrane that's kind of dividing the two. So that is to say urea cannot cross, but water can. So when you take a look at the urea concentration, you have a higher urea concentration on this side and a lower urea concentration on this side. So which direction is water going to go? So a solute sucks. So the highest solute concentration side is where, left or right? So to be right, so then water is going to chase that concentration, isn't it? And that's what you can see. So you can see the difference here in the volume. So here's the volume here versus the volume here. So that volume difference is water flooding into one side, attempting to equilibrate everything. It wants to make everything the same concentration. So that's basically how you move water around, right? So water doesn't just move around because you want it to. Physiologically, we want water to be in certain places in our body, but it doesn't go in certain places. Water does what it wants to do, and it always wins, right? So the way that we actually get water to move into specific places in our body is literally to use this idea, this solute idea to basically get water to move by adding salt concentrations and getting it to chase the salt. That's basically how we get water to move through our body. So since water is chasing salt, then that suggests that different salt concentrations will have different effects on water, right? And that's kind of where we get to what's called our tonic environments. And so we have 3 different types of tonic environments. So tonic basically means salt. Okay. So you have 3 major salt environments that you can get osmotically. I'm going to take a look at a cell, okay, in its surroundings. Like you just put a cell in a pond or whatever, or a beaker or whatever. It's just a cell in its surroundings. And in a hypertonic scenario, this is a situation where there's solute concentration outside the cell is greater than your solute concentration inside the cell. So in a hypertonic scenario, which direction will water move? Yeah, it's going to move outside, right? Now in a hypotonic situation, your solute concentration outside the cell is less than your solute concentration inside the cell. So in this particular case, where is your water going to move? Yeah, it's going to go inside now, right? And in an isotonic situation, your solute concentration outside the cell is equal to your solute concentration inside the cell. So in this case, which direction is your water going to move? Yeah, there's no net movement, right? So it's going to be going both. It'll be exchanging, but there will be no net movement. So that basically means 2 will come in, 2 will go out, 3 will come in, 3 will go out, right? So you have molecules mixing around, but you don't get an accumulation of water either inside or outside the cell because it's the same. This is equilibrium, basically. And so these are your three major types of tonic environments. And depending on which one you get is going to get water movement. So when water wants to move in response to one of these environments, then your aquaporins, right, which are your channels that are open, are what allows the water to move. So this is actually how water moves. All you do is basically move your salt piles in different areas, create different hypertonic scenarios, and you just let water freely go through its open channel. Okay. So you just let it chase down whatever salt it's looking for. Now, one of the things that we see in terms of osmotic pressure is the actual concept of what osmotic pressure is, which is this right here, right? So the force needed to stop osmotic flow. And a lot of times for students, that doesn't make a lot of sense to them, right? But what this is doing is it's using one of those Newtonian principles, right? Remember when you said that every action has an equal and opposite reaction? Remember that one in physics? It was just like physics 1, right? Basic physics, Newtonian stuff. So what does that mean? Well, what that means is if I want to know how much force this door is exerting, I can't measure the amount of force the door is actually exerting, but what I can do is I can oppose the door's force until it's exactly equal. And then if I can measure my force that I'm opposing it with, then that is equal to the force of the door pushing back on me. Equal and opposite reaction forces, right? That's what osmosis is. So that's what osmotic pressure is. So what happens is you can't necessarily measure the pressure of the water, but what you can do is you can oppose that flow and then measure the force that you're exerting on it to get that flow to stop flowing. That is equal to the pressure of the water flowing towards you. And that is a direct result of the sucking effect that the salt has, right? So remember, water is flowing in a cell because it's responding to some salty environment. It's like it's sucking the water toward it. Well, if you want to know how strong that sucking is, then just stand in the way of the water and put your force against it and measure it. If it's really strong, that means that salt pile is really sucking hard on the water, right? So that's basically how you kind of measure osmotic force, but it's related to, it's directly proportional to the suckiness, if you will, of the salt that's sucking the water toward it. And so that's so that's always something that every organism is trying to deal with, right? This osmotic balance idea, where you're trying to basically counterbalance your osmotic pressures and trying to keep yourself from getting too much fluid pressure that will basically blow you up, right? So that's exactly what's happening when we had our contractile vacuole, right? So you're just basically trying to balance your water and make sure you're not going to burst. If you're an animal cell, since you don't have a cell wall, then you're just going to fill up with water in the wrong environment and you're going to explode, right? So you can take on water, but if you take on water, then there's going to be some consequences to that. So this is what those consequences are between an animal cell and a plant cell. So if you take a look at the hypertonic scenario, remember, this is a situation where it's salty on the outside, not on the inside. So all of that water is going to get sucked out of the cells. So if we have, like, for instance, red blood cells, it's going to shrivel up our red blood cells. And so that's not going to be a good thing. That's dehydration. For a plant cell, it's also bad. It's plasmolysis. So basically where all the water leaves the vacuole, and then this membrane starts to suck in and dehydrate. So this is a plant, this is what's called a plasmolized plant. So this plant is basically like flat on the ground. not happy at all, right? This is not a very happy plant. What if we kick it up to the isotonic, right? Make it equal inside and outside. Well, for us, that's great, right? For animals, that's perfect, right? So we get like equal exchange of water in and out. Our cells are happy, right? We're not gaining or losing water. So we're not dehydrating, we're not bursting. This is a perfect thing. So this is our happy spot for animals. This is not so much for plants. This is also do my advanced smiley face rating here, right? So, however, for isotonic, you're still exchanging water in and out, but there's not a lot of water coming in, right? So there's still a lot of slack on the walls. This is what's called the flaccid cell. This is a wilty cell. This is a wilty plant. Still not happy. You can do better. Why? Because you've got cell walls. You can accommodate more pressure, more water pressure in this particular one. For animals, let's kick it up to hypotonic. Not good, right? All of a sudden, inside the cell looks saltier than the outside. Water comes rushing in. It's going to swell us up like a water balloon and lyse it. So this is basically what will create an anemia type of scenario. Because you're killing all your red blood cells. They'll just basically burst. Okay. So that's a bad thing if you're an animal cell. This is what, by the way, would happen to that paramecium if you didn't have that little contractile vacuole to basically pump himself out. Okay. Now, what about the plant cells? Well, the plant cells, all this water is rushing in, and all this water pressure is pushing against the walls. So you can see these walls are buckling outward. They're really strong and solid. This is what's called a turgid cell. This is a nice, happy cell. This is what you want to be if you're a plant. What's the difference? Cell wall. Right. This is one of the reasons why a plant can accommodate and kind of have a lot of adaptability to different salinities in the soils, right? Because they've got cell walls that they can lean on, that can give them a little bit more plasticity. An organism like us, an animal cell with no cell walls, we get into the wrong salty environment and it's just like, we just blow up and die. That's not a good thing. That's one of the reasons why this idea of maintaining osmotic balance is, I always put this in the same grouping as the big biological questions of life, right? Because you have to be able to do this, because for the most part, nobody is in an isotonic environment. So if you're a marine organism, what do? Basically, you have to adjust your internal salt, your internal salinity to match seawater. And you've got an entire physiology, if you're a saltwater organism, that's designed to match your salty sea environment. If you're a terrestrial like us, what about us? Well, we're not surrounded by water, right? So we don't have to worry about that. So what we do is actually we create an isotonic fluid, our blood, and we circulate that through our tissues. So that's the way we do it. So rather than matching our environment, we create our own isotonic solution and we just basically circulate it through our body. But it's important, right? Because we have to maintain that isotonic state in order to be functional. A plant has to maintain what's called turgor pressure, right? That's that water pressure pushing against the cell walls to keep them nice and perky. That's all part of plant physiology if you get into plant physiology. But you notice everybody's touched by this need to balance your osmotic balance. If you're a marine organism or a freshwater organism, same thing, right? This is one of the reasons why saltwater fish die if you put them in a freshwater tank, is because internally they're designed to match a more saline environment. So what's happening is you're putting them in a hypotonic solution. So physiologically, they just blow up, basically. Terrible way to go. Right. So that's your passive transport. Now, what about active transport? So we said active transport requires energy. And the first one we have, and the most important one, is ATP, right? So basically, ATP is our energetic molecule. And so this, in case you're going to be moving things uphill from an area of low to high concentration. And generally speaking, you're looking specifically at carrier proteins. So these carrier proteins are actually going to be very specific. They're going to be carrying and looking for very specific molecules. Like, for instance, if you're building a calcium concentration gradient, then there's a calcium pump that does that. Then the pump is usually what we refer to as the carrier that builds the concentration gradient. So these guys will build concentration gradients for whatever molecule it is that we need a concentration gradient for. So there's different types of these carrier proteins depending on what they move. So the first one you'll see is what's called a uniporter, where you're basically moving a single molecule at a time. So you'll basically see one carrier, and that'll move a particular molecule. A symporter will be moving two molecules, generally in the same direction. Sim means same. So in this case, you'll see something that looks like this. So you'll see this one going in one direction, and you'll see the square one going in the same direction. So that's a symporter. Then antiporters, you're moving two molecules, but it's going opposite directions. So in this case, what's going to happen is you've got your antiporter, and you've got your triangle molecule, which is going one way. And you got your square, which is going the opposite way. And it depends on what you're doing, right? You have a combination. You'll see both. You'll see all of these actually in varying versions and in varying types. But notice, and then you're always moving from low to high. So even if you're an antiporter, what that means is you got two concentration gradients that are pointed opposite each other. Right? That's basically what that means. So let's take a look at the poster boy. This is also one that's going to feed into your AMP1. Because we already talked a little bit about the sodium pump. Excuse me, the sodium concentration gradient, right? We already talked a little bit about sodium going through a sodium channel and going from high to low and the consequences of that. So how did you actually build that grade in the first place? What's the sodium potassium pump that did it? Now, the sodium potassium pump is the classic ATP driven type of pump. It requires a molecule of ATP. We're going to see the mechanism of this here in just a second. In order to do this, it's going to exchange 3 sodiums for 2 potassiums, and they're going opposite each other. It's an antiporter. So they're going to be going opposite direction of each other against their concentration gradient. So this is a situation where the sodium concentration gradient is pointed against the potassium gradient. So they're kind of in opposite directions of each other. But you're going to be using ATP for this particular purpose. So let's take a look at the mechanism. So I want to start off with refer as the native conformation. Conformation simply means the shape of it. So you'll notice here that in its native conformation, it's going to be open to the inside. And in this state, there's going to be 2 sets of pockets, active sites. The first set, which is going to be open for sodiums, are going to be nice and cushy, and they're going to be available for sodium. Okay. The potassium ones are not in this conformation. So think about it this way. The sodium active sites are going to be like nice, cushy little soft chairs, right? Like a good recliner. Right? You just kind of want to sit in it and just sort of melt in it, right? Who doesn't want to sit down after a long day on your feet all day long? Right. So that's kind of what the sodiums are like. The potassiums are a little bit different. At this particular state, they are not happy. They're not friendly sites, right? Matter of fact, when potassium comes in to take a look at its chair to sit down in, what it sees is a bunch of knives coming out of the chair. Right. So basically what that means is you've created a scenario here that is very, very hospitable for sodium to sit down in its pocket, but not for potassium. So the first step then is with consumption of ATP, you get hydrolysis of ATP. Notice you're going to hang on to the phosphate at this particular point. So first of all, your sodiums will bind. So your sodiums sit down, and then comes in ATP, hangs onto the phosphate. And then when that phosphate happens, you get that little energy burst, it creates a shape change. So it's going to change out from underneath you. And so this is basically what happens. So the sodium potassium pump then basically changes from its native conformation to now what's called its alternate conformation. Or its alternate shape. Now this one is a little different. All of a sudden now in the alternate conformation, the sodium sites are the ones that are inhospitable. So imagine it. Here's your sodium, right? It's been a long day. You've been on your feet. You're sitting down in this nice cushy little chair, like at the mall or something like that, right? You get little massage chairs. Right? You're just kind of sitting down in there. And then all of a sudden, you start to feel daggers come up out of your seat, poking into your backside. How long is it going to take you to stand up? Yeah, it's not going to take you long at all. You're going to get it very quickly. Why? Because your seat is changing underneath you. Why? Because it is changing shape due to that phosphate group. But at the same time, the potassium seats are becoming hospitable. Now, those knives are retracting and the chair is looking nice and comfy. So in this alternate state, it's switched to the opposite. Inhospitable sodium seats, hospitable potassium seats. So the sodiums immediately get kicked out. Where do they get kicked out? On the opposite side, outside. But now that the comfy seats are for potassium, what does potassium do? It sees its seat and it's like, oh, hey, these are nice, comfy little chairs. Let's go ahead and bind there. And I'm going to sit down in this nice, comfortable little chair. Notice that alternate state, the comfy chairs for the potassium is held by the potassium. By the phosphate, right, that's in there. But now what happens is the phosphate leaves, and then guess what happens? You basically go back to your native conformation. So what happens to your potassiums? As soon as you sit down, all of a sudden, your phosphate leaves, and then here comes the knives. And then what do? You jump up, right? And at that point, it creates another shape change. Back to your native conformation, and your potassiums jump out. Notice what happened is your potassiums went from outside in, while your sodiums went from inside out. And that starts you all over again. So now all of a sudden, the sodium chairs are nice and cushy, ready to grab onto 3 more sodiums. And so you basically go through this whole oscillation where you have your native conformation, you bind to your sodiums, then you hydrolyze ATP. That phosphate will cause you to change shape, and then you open up to the other side, you dump your sodium, pick up your potassiums, and then you let go of your phosphate, and then you change shape, you dump your potassiums, you pick up some more sodiums, and then you get a phosphate, and you change shape, you dump off your sodium, and you pick up 2 more potassiums, and you just keep going back and forth. And what's changing your shape? the phosphate that's associated with ATP. So you can see almost like this little pump is just basically like grabbing onto it, shape change, dump, grab, shape change, dump, grab, shape change, dump, grab, shape change, dump. You can kind of see it like a bucket brigade going back and forth. And that's all it's doing. It's just doing this its entire existence. Okay. So that basically is your classic ATP driven. And then the indirect version we have is called coupled transport. So this one will actually use the concentration gradient. The example we use here is a glucose sodium symporter. And it uses energy from a sodium concentration gradient to move glucose. And this is kind of what it looks like. So here you can see, here's your symporter. So first of all, you're creating the sodium concentration gradient with your sodium potassium pump. That's why it's indirect. But now what happens is when you have this sort of indirect, what happens is as sodium moves down, it releases energy. And then as it releases that energy, it's transferred to glucose. And that energy transfer to glucose is what powers it up its concentration gradient. So this is a symporter. But what I actually like to use more like is, I like to use an example of an anti-porter better. And so here's how I want to do this. Like imagine we're like two hikers on a trail, right? And I'm going downhill. And of course, downhill, I'm releasing a lot of kinetic energy, right? And so there's a lot of momentum. Matter of fact, if you got a 100-pound pack on your back, there's not a lot of work to going downhill. It's just like a controlled fall, right? You just sort of stick your foot out there, you just sort of land on it. That's kind of what you do, right? But let's say Mobina's going up the hill. And so she's also got a 100-pound pack. So she's doing a lot of work now, because she's having to basically add a lot of her energy into it in order to go uphill. So her energy metric is the opposite of mine, right? So she's consuming a lot of energy to go up. I'm expending a lot of energy to go down. But let's imagine that as I go down, what I do is I give Mobina a little bit of a boost. And so as I'm going down, like a little judo move, right, a little martial arts move, which is notorious for like transferring your body momentum in order to get your assailant off balance so that you can get leverage on them. Let's imagine I do a similar sort of a technique where in this case, as my momentum is being shed as I'm going downhill, what I'm going to do is I'm going to grab onto Mobina as I pass by, and I'm going to transfer my momentum into her and kind of like shove her uphill, right? So for even a few steps, anyway, those few steps are maybe a little bit easier to take, right? Why? Because I've used my momentum, my free energy that's just getting shed as I'm going downhill, and I transferred it to her and I gave it to her so that she could have a couple of easier steps. Basically, I kind of shoved her uphill. That is what I did, right? But that will be an example of what's happening here. So if I already have energy in me, like say for instance from a concentration gradient, then as I'm going from high to low, that momentum that's already being shed, that energy that's already being shed, I can transfer to another molecule to power that one up its hill. Okay. So a concentration gradient can be a very valuable source of energy. But typically it is also built by by ATP, right? So that's the reason why directly it's not energized by ATP, but indirectly it's energized by ATP. Most of your energy is coming from the concentration gradient. So the last bit that we have is bulk transport. But what I will do is I will cover bulk transport on Wednesday. Because we're at the beginning of it, it's going to take a few minutes to kind of unpack, and we're already at our witching hour. So I will stop there, and we'll pick up with that and finish up the last few slides, and then we'll dive directly into chapter 10. And that's where most of Wednesday will probably be spent.